As we transition from our previous discussion, let's delve into the fascinating world of secure application development through the lens of the OWASP Application Security Initiative. This initiative serves as a robust foundation for software engineers and application security professionals, providing essential resources that bolster web security. By understanding the best practices and principles outlined by OWASP, we can significantly enhance our ability to identify vulnerabilities and protect our applications from potential threats. This approach not only safeguards user data but also builds trust in the software we develop. Now let's explore the foundational aspects of application architecture, starting with an introduction to the key components that make up secure framework. Understanding these elements is crucial as we move forward in our discussion of attack surfaces and how to mitigate risks effectively. As we transition from our previous discussion on the OWASP framework, let's delve deeper into the critical aspects of agentic applications. This slide outlines the key components that make up their architecture and highlights some vital considerations for security. We'll explore the core elements that define agentic architecture, which is essential for understanding how these applications operate and interact with users. Next, we'll examine the attack surface, an important concept that underscores potential vulnerabilities that could be exploited. Additionally, we'll touch on the various security patterns that can be implemented to safeguard these applications, along with guidelines for developers to follow throughout the build and deployment process. By grasping these concepts, we can better appreciate the significance of robust security measures in the evolving landscape of AI applications. Now, let's introduce agentic applications and their transformative role in AI development. As we transition from our previous discussion on the foundational elements of agentic architecture, let's delve into the exciting realm of agentic applications. Agentic applications represent a remarkable shift in the landscape of AI development. Powered by advanced large language models, these systems possess the ability to operate autonomously, utilizing various tools and maintaining memory across multiple sessions and users. Unlike traditional applications that follow predictable paths, agentic systems showcase a level of reasoning and planning that allows them to navigate complex workflows seamlessly. These applications not only remember past interactions, but also enable collaboration among multiple agents to achieve intricate tasks. With this evolution comes a responsibility. Our goal is to equip developers and security professionals with practical and actionable security guidance. This will empower them to safeguard these innovative systems against emerging threats. Now let's discuss the scope of our audience and how we can tailor our insights for those involved in building AI systems. As we transition from our introduction to agentic applications, it's essential to define the scope of our discussion. This guide is specifically tailored for a diverse audience, including software engineers who are building AI systems, AppSec professionals tasked with securing applications, and security architects responsible for designing robust defenses. We'll delve into crucial aspects such as secure architectural designs, lifecycle developer guidelines, threat analysis, and mitigation strategies. Additionally, we'll explore runtime hardening techniques and deployment security controls. It's important to note that while we assume some familiarity with application security fundamentals and basic AMM concepts, the focus here is on practical implementation. We aim to provide you with actionable insights, complete with code examples, architectural diagrams, and real-world scenarios for crafting effective agentic systems. Next, we'll connect these concepts to the OWASP security framework, exploring what threats to mitigate and how to catalog them effectively.
As we continue from our discussion on the targeted audience, let's delve into the relationship between the OWASP security framework and the essential strategies for mitigating risks associated with agentic applications. In this context, we focus on cataloging vulnerabilities and attack vectors, utilizing the ASI Red Teaming Guide as a vital resource. This guide provides methodologies for effectively testing defenses, ensuring that security controls are validated and robust. Additionally, the implementation guide offers practical insights on building secure systems, presenting essential controls, patterns, and best practices. Together, these elements create a powerful triangle of builder, defender, and attacker perspectives, ensuring comprehensive application security throughout the entire development lifecycle. In our next discussion, we will explore the 6 core components of agentic systems, which play a crucial role in enabling autonomy and security in application development. Let's dive into that now.
As we transition from our previous discussion on mitigation strategies, let's explore the core components that make up agentic systems. These applications rely on 6 essential elements that empower them to behave autonomously, which is crucial for identifying potential attack surfaces and implementing robust security controls. First, we have the cognitive foundation, enabling reasoning and understanding. Next, orchestration plays a vital role in controlling the flow of tasks, ensuring everything runs smoothly. The ability to strategize and plan comes from the reasoning and planning component, which guides decision making. Additionally, memory modules are essential for persistent knowledge storage, allowing systems to learn and adapt over time. Tool integration ensures these applications can connect with external systems and automate processes effectively. Lastly, operational environments define the runtime context, setting the boundaries for execution. In our next slide, we will delve deeper into large language models, the cognitive core of these systems, and their role in facilitating natural interactions. As we delve deeper into agentic systems, let's explore the pivotal role of large language models, or LLMs. These models serve as the cognitive core, empowering systems to understand and engage in natural language, reason through complex problems, and synthesize knowledge effectively. The choice of the model directly influences both its functionality and security. For instance, foundation models like GPT-4 and Claude 3 offer broad capabilities, while multimodal LLMs can process various data types including text, images, and audio. On the other hand, smaller language models are designed for specific tasks, optimizing efficiency and minimizing vulnerabilities. However, it's crucial to be aware of the challenges these models face, such as hallucinations, misalignment, and susceptibility to manipulation through adversarial inputs. Next, we'll discuss the orchestration layer, which plays a vital role in managing task flow and agent coordination. Let's see how it all comes together. Building on our previous discussion about large language models as the cognitive core of agentic systems, let's now explore the orchestration layer. This layer plays a crucial role in managing how tasks are executed, coordinating agents, and routing decisions effectively. Think of the orchestration layer as the conductor of an orchestra, ensuring that each musician, representing different agents, plays their part harmoniously. It defines the interactions and collaborations among agents, helping them maintain consistency even in complex workflows. We can identify several approaches here. Linear workflows allow for straightforward task execution, while hierarchical planning enables master orchestrator to break down complex tasks for specialized agents. Additionally, multi-agent collaboration allows agents to communicate directly to achieve shared objectives. However, it's important to be aware of potential vulnerabilities such as intent manipulation and identity spoofing, which can disrupt these workflows. Next, we'll delve into the critical roles of reasoning and planning in empowering agents to tackle complex problems effectively.
Building on our previous discussion about the orchestration layer, we now turn our attention to reasoning and planning mechanisms, which play a crucial role in how agents tackle complex problems. These mechanisms empower agents to decompose intricate tasks, evaluate various solutions, and ultimately make informed decisions regarding tool usage and task execution. One effective approach is the chain of thought, which encourages step-by-step reasoning, allowing for clarity and transparency throughout the decision-making process. The React pattern illustrates how agents can adapt their actions based on feedback from tools, fostering a dynamic interaction with their environment. Additionally, the tree of thoughts helps agents explore multiple reasoning pathways, ensuring they arrive at the most optimal solutions. However, it's essential to be aware of potential security concerns, such as cascading hallucinations and manipulative reasoning, that could undermine the integrity of decision-making processes. Next, we'll delve into how memory architecture enables agents to maintain a persistent state, learn, and share knowledge effectively.
As we transition from our discussion on reasoning and planning, let's delve into the fascinating realm of memory architecture. Memory systems play a critical role in agentic applications, allowing these agents to maintain a persistent state, learn from experiences, and share knowledge effectively. We can think of memory in a few distinct categories. First, there's short-lived context memory, which is cleared after a session, ensuring that only relevant information persists. Next, we have user-specific memory, which allows for a personalized experience by retaining knowledge tailored to individual users. And there's shared memory, which facilitates collaboration between agents, enabling them to work together seamlessly. System-wide memory provides broader insights while maintaining user anonymity. Lastly, vector databases support external knowledge, enhancing the agent's capabilities. However, it's essential to acknowledge the security challenges this memory architecture presents, such as memory poisoning and potential data leaks. Up next, we'll explore how tool integration frameworks can connect these agents to external systems, further enhancing their functionality.
Building on our understanding of memory architecture, let's now explore tool integration frameworks. These frameworks play a critical role in connecting agents to a variety of external systems, facilitating everything from straightforward API calls to intricate automations. The flexibility of these frameworks is impressive, but it also brings significant security considerations. For instance, there are extensive tool libraries available, such as LangChain and AutoGPT, each with varying levels of security maturity. Then we have managed platforms like AWS Bedrock and Microsoft Copilot Studio, which provide robust security features but limit customization options. Lastly, hosted solutions like OpenAI Assistance API and Claude Tools come with built-in guardrails to enhance safety. However, it's important to be aware of high-risk areas, including untrusted tool execution and potential privilege escalation through API abuse. Next, we'll delve into how the operational environment shapes the boundaries and capabilities of these integrations. As we transition from our exploration of tool integration frameworks, let's now turn our attention to the operational environment of agentic systems. This environment is fundamental as it outlines the boundaries and capabilities that are available during runtime. Understanding these operational dynamics is essential for implementing effective security measures and containment strategies. For instance, the API access layer enables seamless system integration through interfaces like REST, GraphQL, and WebSockets, but it necessitates robust authentication and authorization protocols. Similarly, the execution environment for coding languages such as Python and JavaScript allows for dynamic tool creation and data processing, while database connectivity requires meticulous privilege management to ensure safety. We must also consider web browsing capabilities for tasks like information gathering and automation, alongside the critical infrastructure that supports SCADA and IoT systems. Here, maximum security controls are imperative to mitigate risks like remote code execution and unauthorized access. Next, we will delve into analyzing the attack surface of these systems, particularly in relation to OWASP threats.
As we transition from understanding the operational environment, let's delve into the concept of attack surface analysis, specifically through the lens of OWASP mapping. This approach is crucial in identifying and prioritizing security investments by directly linking threats to the components of agentic systems. In this analysis, various components face distinct primary threats. For instance, large language models may experience hallucinations or misaligned behaviors, while orchestration can be susceptible to goal manipulation and spoofing. Memory systems are at risk of poisoning and privilege collapse, and tool integration can lead to misuse or unexpected code execution. Finally, environmental factors might expose systems to privilege abuse and resource overload. By mapping these threats, we can develop targeted threat models and implement defense-in-depth strategies tailored to address vulnerabilities specific to our architecture. Next, we'll explore how selecting the right architectural pattern can significantly enhance our security posture. As we transition from our previous discussion on the OWASP threats and their mapping to agentic system component, let's delve into the crucial topic of architectural patterns. Choosing the right architectural pattern significantly influences the security of your system while also balancing functionality and complexity. For instance, sequential architecture offers minimal attack surface by utilizing single large language model and straightforward linear workflow. This approach is beneficial for scenarios with limited scope. On the other hand, hierarchical architecture provides good modularity through an orchestrator that coordinates specialized subagents, enhancing flexibility. However, distributed architectures introduce higher complexity, allowing for peer collaboration without central control. The reactive pattern stands out for its responsive workflows but comes with risks, especially concerning data exposure due to external sources. Ultimately, your choice of pattern should align with your specific use case, risk tolerance, and available resources. Next, we'll explore the security profile of sequential architecture, which offers one of the simplest and most secure approaches. Building on our discussion about the secure architecture pattern, let's dive into the unique security profile of sequential architecture. This approach is renowned for being both simple and secure, making it particularly suitable for agentic applications. At its core, sequential architecture utilizes a single large language model as its primary reasoning engine, which streamlines the workflow into linear, predetermined execution path. This configuration not only minimizes complexity, but also establishes strong security boundaries. The use of chain-of-thought reasoning enhances transparency, while the in-session memory ensures that no data persists beyond the interaction. However, while it offers significant security advantages, such as reduced attack surface and easier monitoring, It's important to remain aware of potential vulnerabilities like prompt injection and model hallucinations. Next, we'll explore hierarchical architecture and its security considerations, shedding light on how it contrasts with the sequential model. Building on our discussion of sequential architecture and its security advantages, let's now explore hierarchical architecture and the unique security considerations it presents. Hierarchical architectures employ central orchestrator that manages specialized subagents. This modular approach enhances system capabilities, allowing for tailored functions. However, it also introduces new attack vectors, particularly in areas like identity management and inter-agent communication. The main security benefits of this architecture include the separation of concerns, which effectively limits the blast radius of potential breaches. With centralized control system, there's a single point for policy enforcement, contributing to more manageable security landscape. Additionally, enterprise-grade tooling frameworks enhance overall security and auditability, enabling clear tracing of decisions within the hierarchy. However, we must remain vigilant about risks such as identity spoofing, rogue agents, API misuse, and memory poisoning. Given its complexity, hierarchical architecture is best suited for enterprise applications that require modular capabilities complemented by robust identity and access management systems. Next, we'll transition to swarm architectures, which utilize peer-to-peer collaboration among agents and introduce their own set of security challenges. Building on our previous discussion about hierarchical architectures, let's explore swarm and distributed architectures. These systems leverage peer-to-peer agent collaboration, which means there's no central orchestrator or single point of control. This decentralization offers remarkable scalability and resilience, making it an attractive option for many organizations. However, with these advantages come significant security complexities. The absence of central authority can lead to new vulnerabilities, such as agent collusion and communication channel poisoning. Furthermore, the emergent behavior of agents can make it difficult to predict potential malicious actions, complicating incident response scenarios. Because of these challenges, swarm architectures are best suited for organizations with advanced security operations and high tolerance for complex threats. As we transition to our next topic, we'll examine how the choice of development framework can significantly impact security implications. As we transition from our discussion on swarm architectures and their peer-to-peer collaboration, let's delve into an equally critical aspect: the choice of development framework and its direct impact on security. Frameworks play a pivotal role in shaping not only the security posture of your applications, but also their maintenance and the controls available to you. Each framework comes with its own set of trade-offs and dependencies. For instance, Lakai offers high flexibility and an extensive tool ecosystem, but demands careful management of dependencies and robust security hardening for community components. On the other hand, Creweye is tailored for collaborative agents with built-in role management, presenting moderate security posture that benefits from growing community. Meanwhile, Microsoft Audigen focuses on enterprise solutions, providing strong security integration, albeit with limited flexibility. Lastly, the OpenAI API offers managed service with built-in guardrails, which reduces the burden of security maintenance. However, keep in mind the risk of dependency fragility across these frameworks. Establishing clear security update policies and testing procedures is essential. Now let's explore how developers can ensure security throughout the lifecycle of agentic applications. As we transition from our previous discussion on the impact of framework choices on security, let's delve into our next topic: lifecycle security for agentic applications. Security isn't just one-time task, it's a continuous process woven throughout every stage of development, from design to operations. During the design phase, it's essential to engage in threat modeling and create secure architecture, along with implementing input validation to safeguard against vulnerabilities. When we move to the build stage, practices like static analysis and dependency scanning come into play, ensuring that our code is robust and our environments are hardened against potential threats. Finally, in the operations phase, ongoing vigilance is key. This means continuous monitoring, having solid incident response plan, and utilizing behavioral analysis to detect any unusual activities. Next, we'll explore the importance of secure design practices, emphasizing how adopting secure by design principles during development can make all the difference in creating resilient applications. Building on our previous discussion about the continuous nature of security for agentic applications, it's essential to focus on secure design principles during the development phase. Embracing these principles means we aim to prevent vulnerabilities right from the start, rather than attempting to detect them later. To do this effectively, we employ threat modeling to identify potential attack vectors. Techniques such as input validation and secrets management are vital, as is ensuring least privilege access and managing secure dependencies. Additionally, content moderation plays a key role in automating the detection and filtering of harmful content and personally identifiable information. Implementing memory security through access policies and sanitization can further bolster our defenses. By making these practices standard and enforcing them through automated tools and code reviews, we can create robust foundation for our applications. Next, we'll explore prompt hardening techniques which are crucial for preventing injection attacks and ensuring overall security. As we continue our discussion on secure development practices, let's dive into the importance of prompt hardening techniques. These strategies are essential for preventing injection attacks and ensuring that AI agents function as intended, building strong defense against potential manipulation. To achieve this, it's crucial to implement several core hardening strategies. First, consider delimiter usage. Consistently separating instructions from user input with clear markers helps maintain clarity. Next, creating explicit allow and deny lists defines acceptable actions while forbidding risky operations. Additionally, clearly outlining the capabilities and limitations of your AI agents helps set appropriate boundaries. Providing few-shot examples guides the AI in safe behavior, while thorough input sanitization prevents dangerous concatenation of user inputs. Lastly, regularly testing prompts against known injection patterns ensures that your defenses remain robust. With these techniques, we can effectively secure our AI agents. Now let's explore the unique security challenges posed by memory systems in agentic applications. As we transition from the importance of prompt hardening and safeguarding against injection attacks, let's delve into the unique security challenges posed by memory systems in agentic applications. Memory security architecture is crucial given the persistent nature of memory and the complexity of cross-boundary access patterns. To effectively secure memory, a multi-layered approach is essential. First, we implement end-to-end encryption, ensuring that data remains secure both at rest and during transit, with a strong focus on key management. Next, we emphasize input validation, ensuring that all data is sanitized before it finds its home in memory. We also prioritize the protection of personally identifiable information through automated redaction, bolstered by data loss prevention measures. Human oversight plays a vital role as well, necessitating review and approval for sensitive memory entries. Furthermore, we utilize context isolation techniques akin to the Chinese wall principle and enforce lifecycle management practices including TTL expiration and automatic data cleanup. With these robust strategies in place, we're setting the stage for our next discussion on integrating security seamlessly into the build and deployment pipeline. Let's explore how this integration can fortify our applications even further. Building on our previous discussion about memory security architecture, let's delve into the essential practice of integrating security into the build and deployment pipeline. In today's fast-paced development landscape, this integration is vital for safeguarding agentic applications against vulnerabilities before they even reach production. First, we employ static application security testing to identify code-level vulnerabilities and insecure patterns right from the start. Next, we turn our attention to managing open-source dependencies, ensuring we detect and address known vulnerabilities early in the process. Environment hardening is equally important, where we isolate environments using containers and sandboxing techniques to minimize risk. We also emphasize the secure management of credentials and API keys along with scanning for any infrastructure misconfigurations. Finally, specialized AI testing helps us validate agentic behavior through techniques like prompt fuzzing and adversarial testing. By implementing these automated security gates, we ensure that only applications meeting our security standards are deployed. Now, as we shift our focus to runtime security, we'll explore the importance of continuous monitoring for agentic applications.
As we transition from the importance of integrating security into our build and deployment pipeline, let's delve into the critical aspect of runtime security for agentic applications. This involves continuous monitoring, which is essential for ensuring the integrity and safety of these dynamic systems. To achieve robust runtime security, we need to focus on real-time analysis of both traditional application metrics and AI-specific behaviors. This includes monitoring prompts, tool usage, memory, and identifying any behavioral anomalies. Implementing guardrails, such as input-output sanitization and content moderation, helps maintain a secure operational environment. Additionally, executing monitoring through plan validation and sandboxed execution allows us to validate tool call parameters effectively. By employing statistical analysis to detect memory drift, we can identify unauthorized modifications, while machine learning models assist us in spotting unusual patterns in communication and decision-making. Lastly, integrating automated response systems ensures that any security incidents are swiftly contained and remediated. Next, we will explore the role of comprehensive logging and observability in enhancing our security practices.
Building on our discussion of runtime security, let's delve into the critical role of logging and observability in agentic applications. Comprehensive logging is not just best practice, it's essential for detecting security incidents, conducting forensic analysis, and ensuring compliance. In distributed systems, this requires specialized approaches. For instance, integrating platforms like Langfuse, Langsmith, and MLflow can provide a holistic view of model performance and agent behavior. Using structured logging with JSON formats allows for automated parsing and alerting, enhancing our ability to correlate data across various components. Additionally, implementing end-to-end request tracking with unique trace IDs helps us follow the journey of requests seamlessly across agent boundaries. Importantly, security-first approach is vital. This means employing HMAC-protected immutable logs and ensuring that sensitive information is never logged in the first place. As we transition to the next topic, let's explore the specialized incident response strategies necessary for these dynamic systems. As we transition from our previous discussion on observability best practices, let's dive into the critical topic of incident response for agentic systems. Responding to incidents in these AI-driven applications requires specialized procedures due to their unique challenges. First, it's essential to define clear criteria for what constitutes an AI-specific incident. This can include various threats like prompt injection, rogue agent behavior, and memory poisoning. Once identified, we must implement immediate containment protocols. These steps might involve disabling the agent, revoking credentials, or quarantining affected memory. Furthermore, forensic analysis plays a pivotal role in understanding the incident. By examining reasoning chains and cross-agent communication, we can gain valuable insights. Recovery and remediation are equally crucial. This includes executing system rollbacks and updating security controls. Lastly, regular tabletop exercises are vital for testing these response procedures, ensuring our teams are prepared for any eventuality. And remember, since agentic systems can operate autonomously, having immediate kill switches and automated triggers is essential. Next, we'll explore the complexities of multi-agent security architecture and the challenges it presents. As we transition from our previous discussion on incident response for agentic applications, it's crucial to delve into the architecture that underpins multi-agent systems. These systems, while powerful, present unique security challenges that necessitate thoughtful design to mitigate risks like agent impersonation and coordinated attacks. Proper architecture is essential. One key strategy is ensuring a clear separation between agent-to-agent communication and orchestration commands. This isolation helps maintain control and security. Additionally, strong authentication and authorization measures are vital. Utilizing mutual TLS and tokens and role-based access control can fortify interactions between orchestrators and agents, enhancing security. To detect rogue agents, we should continuously monitor for behavioral anomalies and analyze communication patterns using automated quarantine when necessary. Implementing robust communication security protocols such as message signing and replay attack prevention is equally important. Lastly, controlling inter-agent communication through rate limiting helps prevent denial of service attacks and identifies unusual behaviors. In our next discussion, we'll explore the concept of runtime hardening, which adds another layer of defense for agentic systems. As we transition from our discussion on multi-agent systems and their complex security challenges, let's delve into the concept of runtime hardening. This approach is essential for providing defense and depth protection for agentic applications. By implementing independent controls and critical backstops, we can significantly limit the impact of successful attacks. To achieve this, consider container hardening using established benchmarks and maintaining a minimal attack surface. Regular patching and host-based intrusion detection are also key practices. Additionally, memory isolation techniques similar to Google's Camel style help safeguard execution contexts. It's also vital to ensure that outputs from untrusted large language models undergo thorough scanning and validation before any further processing. Moreover, dynamic code execution environments should be properly sandboxed, enforcing strict resource limits and network restrictions. As we move forward, we will examine the significant supply chain risks that agentic applications encounter, particularly in the realm of AI frameworks. As we transition from our discussion on runtime hardening, let's delve into pressing concern for agentic applications, supply chain security risks. These applications are uniquely vulnerable due to their reliance on evolving AI frameworks, model dependencies, and third-party integrations. The landscape of AI is constantly changing, and with it comes the challenge of maintaining security. For instance, rapidly evolving frameworks like LangChain or CrewY can introduce unforeseen vulnerabilities. Additionally, pre-trained models may harbor hidden backdoors or biases, while third-party APIs can vary significantly in their security maturity. Moreover, external knowledge bases and content sources are not immune to risks such as poisoning. To mitigate these threats, it's crucial to implement continuous vulnerability monitoring, supply chain verification, and regular security testing. In essence, protecting the integrity of our systems means understanding these risks and reinforcing our defenses. Next, we'll explore the specialized techniques required for red teaming agentic systems, highlighting the unique challenges they present. As we transition from discussing the supply chain risks associated with AI frameworks, let's dive into the complexities of red teaming for agentic applications. Unlike traditional penetration testing, red teaming for these systems requires a specialized set of techniques to effectively identify vulnerabilities. These applications possess unique reasoning abilities and access to various tools, opening up new and unexpected attack vectors. For instance, prompt injection testing explores how malicious inputs can manipulate responses, while memory poisoning examines the injection of harmful content that may alter future agent behavior. We also investigate tool misuse, looking for ways to escalate privileges and execute unexpected code. Furthermore, we consider the potential for multi-agent collusion, testing how coordinated attacks among agents could circumvent security controls. Next, we'll explore a compelling case study that highlights the security strategies implemented for multi-agent copilot systems, showcasing real-world applications of these techniques. Building on our previous discussion about red teaming agentic systems, let's delve into a practical example: multi-agent copilot security. This case study illustrates how security is implemented within a multi-agent enterprise copilot system that seamlessly integrates with various productivity tools. At the core of this system is the orchestrator agent, which manages task decomposition and workflow coordination. Specialized subagents handle specific functions like calendar management, email communication, and ERM integrations. A shared memory system ensures that context and user preferences are accessible across agents, while human oversight is critical for sensitive operations, requiring approval workflows for certain actions. Security measures are robust, including strict parameter schemas for tool interactions and scope permissions to limit access. While these controls are vital, they highlight the balance between security and user experience. As we transition to our next topic, we'll explore key takeaways for practitioners, emphasizing the essential shifts needed in securing agentic applications. As we transition from our earlier discussion on the case study of multi-agent application security, let's focus on a crucial takeaway for practitioners. Successfully securing agentic applications requires a fundamental shift in our approach to application security. Unlike traditional systems, these applications create unique attack surfaces that call for innovative defensive strategies and ongoing vigilance. It's essential to recognize that conventional security tools often fall short when it comes to vulnerabilities like memory poisoning or tool misuse. To address these risks effectively, we must implement security measures at every stage of an application's lifecycle, from design to deployment. Retrofitting security later on can be both costly and ineffective. Moreover, a comprehensive security strategy must integrate sandboxing, guardrails, monitoring, and human oversight. No single control can offer complete protection, especially in light of the evolving threat landscape. As we move forward, we'll explore additional resources, including the OWASP security framework, which can provide further insights into securing agentic applications. As we transition from our previous discussion on securing agentic applications, it's crucial to highlight some valuable resources that can further enhance our understanding and implementation of these strategies. The OWASP security framework provides a comprehensive guide specifically designed for securing agentic applications. This includes vital resources such as the OWASP Top 10 for large language models, which outlines key vulnerabilities, and the Agentic Threats and Mitigations Guide that offers targeted strategies to address these challenges. We also have some powerful security tools at our disposal, like LlamaGuard for content safety classification, NVIDIA Nemo guardrails for programmable oversight, and the OpenAI Moderation API or effective content moderation. In addition to these tools, there are essential testing resources and industry standards like the NIST AI Risk Management Framework and ISO 27001. 2022, which ensure compliance and best practices in AI security. Next, we'll open the floor for questions and discussion, so feel free to share your thoughts and inquiries. As we wrap up our discussion on the OWASP security framework and the essential guidelines for securing agentic applications, I want to take a moment to thank you for your engagement and curiosity. This slide invites you to continue the conversation with questions and insights. We encourage you to explore the OWASP Agentic Security project page for valuable resources and the latest updates on security practices. Staying informed is key to maintaining a secure environment. Remember, security is not just a one-time effort, it's an ongoing commitment. So let's keep the dialogue going. If you have thoughts or queries, now is the perfect time to share. And as we look ahead, we'll delve into practical steps you can take to enhance your security posture. Let's keep the momentum going.